we often say that electricity is the fuel of economic growth, but today's reality is even broader. Electricity is becoming the backbone of India's manufacturing ambitions, digital economy, mobility transitions, and clean energy future. The question is therefore no longer whether India can generate enough electricity. The real question is, can our power infrastructure evolve fast enough to carry, manage, and optimize this new energy landscape? I believe that is where the smart electrification truly begins. India's electricity demand is entering a new phase. There are several structural changes taking place simultaneously, such as manufacturing led growth, with initiatives such as Make in India, PLI schemes, and development of industrial corridors. Electricity demand from manufacturing is expected to rise substantially. New industries such as semiconductor fabrication, electronics manufacturing, advanced materials, high quality power. All these require high quality power. Manufacturing competitiveness is now directly linked to reliability of electrical infrastructure. Second is the digital economy. AI, cloud computing, fintech, and hyperscale data centers are among the fastest growing consumers of electricity. Unlike traditional consumers, data centers require 24/7 reliable supply, net zero interruptions, high quality voltage, and increasingly renewable source of power. This means electrical infrastructure is becoming a strategic component of the digital infrastructure. The third component is digital mobility. Electric vehicles are changing the way electricity is consumed. Traditionally, power flowed from large generating stations to consumers in predictable patterns. Now the theme has changed. Development of EV charging infrastructure introduces new demand centers, higher peak loads, fast charging requirements, and greater uncertainty in load profiles. Therefore, distribution networks must become smarter and more responsive. Renewable energy, the growth in installed capacity of solar and wind in India in the recent years have been remarkable. However, this comes with its own set of challenges. Solar generation peaks during the day, whereas wind is unpredictable. Balancing the demand and supply has become increasingly very complex. This is where transmission planning, storage, and digital control systems become very essential. A generation target of 900 gigawatt of by 2035-2036 of non-fossil fuel capacity has been set by the government. To support this target, a comprehensive transmission plan has also been prepared by the CEA. Further, National Generation Adequacy Plan by the CEA envisages energy storage installations of 174 gigawatt by 888 gigawatt hour, which includes a battery energy storage of 80 gigawatt by 320 gigawatt hour and a pump storage of 94 gigawatt by 567 gigawatt hour. Transmission becomes the backbone of India's energy transition. As India accelerates its energy transition, one fact has become increasingly clear. The success of our renewable energy ambitions will depend as much on our transmission network as on our generation capacity. Today's grid must accommodate large scale renewable energy, distributed generation, battery energy storage systems, and growing interstate power transfers. Manufacturing facilities, metro rail systems, airports, hospitals, and hyperscale data centers all will require uninterrupted, high quality power. The modern transmission network must therefore be designed not only for capacity but also for resilience. Further, technology is redefining transmission. So, by adopting practices like digital substations, fiber enabled communication systems, real time monitoring, AI assisted analytics, drone based inspections, and predictive maintenance tools, they help the transmission become more digitalized. Now, coming to the grid digitalization and integration of the IoT, that is Internet of Things. So, as grid becomes larger, more interconnected, and more complex, it must also become more intelligent. The future power system will not simply transport electricity, it will continuously monitor itself, communicate in real time, predict failures, and optimize operations. That, in essence, is what grid digitalization is all about. The IoT is transforming how utilities monitor and manage assets. Rather than waiting for a scheduled inspection, utilities can now collect operational data continuously from the field. So, I will start with the challenges that the utilities are facing and how we have been able to overcome those challenges growing in the space of technology. The first challenge that the utilities have been facing is the non-availability of data. Without real-time and accurate data availability, planning for a stronger grid often becomes challenging. This is where the requirement of asset mapping with technologies like geotagging and GIS-based systems is necessary, where it will help us in knowing exactly the position of assets and the entire network of assets. The second challenge is that in many areas we have not shifted in from a radial network to a ring main network. So it is important. Earlier, we did have a one directional flow of power, which has now become bidirectional because of distributed energy resources. We have seen multiple tripping events in our Gujarat, in some regions of Gujarat where there is excess RE generation. Thus, that network design should be ring main to accommodate any failures and minimize the downtime. Now, once the backbone has been grown strong, we come to the grid modernization. Of course, right now we are seeing a mass rollout of smart meters at consumer level, but there is a lot more to smart grid also. Starting at substation level, we have solutions like smart feeder monitoring solution or SFMS. It gives us useful data for outage management and helps us plan networks efficiently and gives real-time data availability with authentic data for feeder tripping, network load growth check, and equipment health monitoring. Now we come to switch gears. We have been able to modernize switch gears such as ring main units, sectionalizers, and auto reclosures. With these systems, self decision is being made without human intervention. A classic example is the installation of an automatic transfer scheme or ATS at the Micron semiconductor unit in Sanand. The client's requirement was to restore power before 30 seconds. Hence, the equipment was installed in the RMU of the system, and it was given two sources of power. So with the help of voltage passage indicator and fault passage indicators, the system has been implemented and it has been proven success. This also becomes a future for hospitals, schools, and many important areas. Now coming to the transformer level, we have seen issues of over voltage and under voltage in the high RE zones. Remote monitoring systems with automatic tab changing are also being used to resolve the systematic issues being faced today. Networks should be designed such that they are capable to run for more than 25 years. An example of this we saw, considering the N-1 redundancy, we must use equipments which are capable to foresee a future of 25 years. So in conclusion, I would say that the next decade will probably be remembered as the decade in which India's electricity sector fundamentally transformed itself. Over the last decade, we have demonstrated that India can add generation capacity at an unprecedented pace. Today, our installed power generation capacity has already crossed 530 gigawatt and is expected to approach 600 gigawatt in the near term. This reflects scale and momentum of our power sector. At the same time, India's non-fossil installed capacity is expected to grow by 300 gigawatt this year, bringing us ever closer to our national target of 500 gigawatt of non-fossil capacity by 2030. But capacity alone will not define success. The real measure of success will be whether every megawatt of clean electricity can be evacuated efficiently, transmitted reliably, and stored intelligently, and delivered securely to the homes, industries, and data centers and electric vehicles across the country. The next phase is all about integration.